Okay, into part B, and in this video we are going to look at how we make a nuclear reactor for a nuclear power plant, and we're also going to briefly look at the process of nuclear fusion also. Okay, I've got a link here, and I'll put this up on Edmodo to the nuclear power plant game, which is worth going and having a little play with, because it sort of gives you an insight into controlling a nuclear power plant. And I've got a diagram here which shows a representation of a nuclear power plant. It actually comes from this game. And essentially we have our reactor here, where we have our nuclear induced fission happening, heating up a coolant. That coolant then goes and heats up another coolant, produces steam. Steam drives a turbine. Turbine produces electricity, and then it goes to cool all that water down, and then that goes back through. The reason we have two coolant loops here is basically a safety thing. We don't want this water that's been turned to steam and going through our turbine being exposed to the radiation in the core, so they sort of separate out those two cooling loops to achieve that. Anyway, so what are the parts of a nuclear reactor? Well, firstly we have our core, as I've said, which is where the reaction happens. Then we have our fuel rods. So in here we have basically fuel rods which contain our uranium-235, and that's all surrounded by our moderator, which is usually water, that surrounds the fuel rods to absorb the energy from the neutrons to slow them down so they can be captured for further fission. So remember, they've got to get slowed from 1 to 2 mega electron volts that they get released at to about 10 electron volts so that they can induce a fission. So there's all moderator surrounding the fuel. Now, importantly, we then need these control rods that can go up and down on the fuel rods, and they are made of a good neutron absorber, and basically they can be lowered over the fuel rods to reduce the number of neutrons available by absorbing some for fission, allowing the nuclear reaction to be slowed, or vice versa. So they can be lifted up to release more neutrons to get the reaction going faster. The delay in the release of neutrons produced during fission assists control the reaction. If the rate of fission gets too fast, potentially causing meltdown, the delay gives time for the control rods to be lowered, hence reducing the rate of fission. If neutron release was instantaneous, the reaction could get out of control before any preventative action could be taken. So that is why the delayed emission of neutrons allows the chain reaction in a nuclear power plant to be controlled. And that's very important in the nuclear power plant example. There's also a heat exchanger, so the coolant is pumped through the core and is heated due to nuclear fission through the core, heated in the red. This coolant then passes through a heat exchanger where it heats water, secondary coolant, to form steam to drive a turbine to produce electricity. So this heats up this water, boom, produces it. You would also, in your nuclear power plant, have safety rods, which are separate large control rods that can be quickly dropped to shut down nuclear fission if a problem occurs. So they're like a second set of control rods. If the control rods fail, they can be released, absorb the neutrons and stop the process. You also need a large amount of shielding around this, as you've got large amounts of radioactivity produced. The core must be encased in steel and concrete to stop the radiation being released. So just going through your intended student learning, there are all the parts of our nuclear reactor and their role. We talked in the last slide about why uranium fuel needs to be enriched, so there's more chance of induced fission than a neutron just being absorbed and not available for the chain reaction. Relate the starting, normal operation and stopping of the nuclear reactor to the nature of the chain reaction. So initially we need a supply of neutrons to get the chain reaction going. Then we need to, in normal operation, control that neutron flux or flow so that it happens in a controlled sense. And then obviously to stop the reaction, we lower the control rods, or in an emergency the safety rods, to stop the neutron flow. And I talked about how the delay allows that reaction to be controlled already. So now, hopefully, not only can you make yourself a nuclear bomb, but you can also make yourself a nuclear fission power plant. And finally, let's talk about nuclear fusion. So nuclear fusion is the process in which two nuclei combine into a single nucleus. So here we have a deuterium, a hydrogen 2, and a tritium, a hydrogen 3, combining to form a helium 4 nucleus and also a neutron. Here we have hydrogen combining through a number of steps to also produce helium. This is the process we use to try and simulate fusion in the laboratory on Earth. This here is actually the process that occurs in the Sun to produce energy through nuclear fission. Now, as with fission, the total mass of the reactants in fusion, the total mass of reactants in a fusion reaction is greater than that of the products, releasing energy. So that mass that's lost is converted to energy by E equals mc squared, where delta M is the mass of reactants minus the mass of products. So, what do we need to do to make this occur? Well, for fusion to occur, high kinetic energies are needed to overcome the repulsive electrostatic force between the nuclei and to allow the nuclei to approach within the very short range of nuclear attractive forces. So normally the protons in this and this would be trying to repel each other. We need a huge amount of energy to push them close enough together so that the short range nuclear force, strong nuclear force, which is attractive, takes over to form a new nucleus. Same here with the two hydrogen forming this, and all of these hydrogen and helium going together to eventually give you a helium-4 nucleus. So, the two main factors that maintain nuclear fusion reaction with the Sun are, firstly, the large mass means the gravitational force is massive, holding the atoms in very close proximity. Because the Sun is so large, has a really large mass, therefore very, very strong gravity, holds everything together really tightly. Secondly, the products of nuclear fusion have huge amounts of kinetic energy, and when they collide with hydrogen atoms, they can transfer some of their energy to them. So, this is a really fancy way, I guess, of saying the Sun is really, really hot, so these particles are all moving really, really fast. So not only are they held together really tight by gravity, they're also moving really fast. That allows them to become close enough to overcome that repulsive electrostatic force and for that strong, attractive nuclear force to take over. Again, these reactions give mega electron volts of energy compared to chemical processes like, say, burning hydrogen gas to make water, which gives you like electron volt type amounts of energy. So yeah, that's the main key points here. You've got to be able to do your E equals mc squareds, understand why you get more energy than a chemical process, and describe those conditions, gravity and heat, therefore high kinetic energies, that allow the fusion process to occur. Just out of interest, this diagram also talks about the amount of energy each particle has. And once again, the energy here is, if you like, inversely proportional to the size. The helium gets less energy due to conservation of momentum. The bigger particle moves slower, therefore has less energy. The smaller particle moves faster, therefore has more energy. If you look at the ratio of these two numbers, it would accord to the ratio of, or it would be the opposite to the ratio of their masses. Don't really need to know this for fusion, but it's a good little reminder of that relationship between mass and the amount of energy a particle gets in any form of nuclear reaction. So finally, just need to briefly outline some of the advantages and disadvantages of nuclear fusion over nuclear fission. as a future power source. Fusion can be done with deuterium, which is basically almost inexhaustible. So we're not likely to pretty much ever run out of our reactants to drive the fusion process. Also, you do not produce any radioactive waste. So we talked about all of the products of nuclear fission themselves being radioactive because of an excess of neutrons. Not the problem with fusion. You make stable isotopes. The chances of meltdown through an uncontrolled reaction are also very unlikely with fusion, well, almost impossible. We can get, if the control rods don't work properly or something in a fission plant, we can have an uncontrolled reaction, and that can cause all sorts of consequences like Fukushima and Chernobyl and some of those others that have been in the news. However, in nuclear fusion, if basically the reactor vessel was corrupted in some way, it's likely you would immediately lose the pressure. Because you lost the pressure, the particles wouldn't have the energy to cause them to collide close enough, so that energy would be, you couldn't have an uncontrolled reaction. Anything that went wrong would basically stop the reaction itself. However, the disadvantage of fusion is the difficulty in maintaining high temperatures and kinetic energies to sustain the reaction. And they haven't yet been able to produce the conditions to make fusion occur on a commercial sort of basis at all on the Earth yet. The Sun does it through its sort of natural processes, but simulating that on Earth in a commercially practical system has not yet been achieved. It's the focus of a lot of research. It's probably still a long way away. It's actually something my son has just done his Year 12 research project on. So if you're interested in that, let me know and I'll let you read more about that. It is quite an interesting area of science. Thank you.